Okay, welcome, good morning, good afternoon, depending where you are in the world. Thanks for joining today. Before we go any further, can I check that people can actually see and hear me? And to test that, please write where you are joining from today in the chat box on the right-hand side. If you could just write a place and country you're joining from, that will be a good confirmation that you can actually hear me. Great, great. So we have all over Europe. We have quite a few universities: Poland, Sweden, Austria. We have India. Great. Santiago, Chile. Amazing. Fantastic. So that works. Great. Thank you. It seems that you can see me, you can hear me, which is a great start. So if you have any problems with the connection during the webinar, please just reload the site in your browser or just use the access link to rejoin the webinar again. So my name is Tomasz Liskiewicz. I'm a director at Surface Ventures, and I'm your host for today's webinar with Professor Allan Matthews. Allan is a professor of surface engineering and tribology in the School of Materials, and director of the BP International Center for Advanced Materials at the University of Manchester. He's a fellow of the Royal Academy of Engineering, and he has been a central role in many professional learned societies, including the British Vacuum Society, the American Vacuum Society, and the Society of Vacuum Coaters, CVC. He's also an editor-in-chief of the Elsevier journal Surface and Coatings Technology, a journal where many of us actually submit our papers. So in terms of agenda for today, we will start in a few minutes with Allan's presentation. Then we will switch for a few minutes to Adrian Harris from our sponsor Micromaterials, and then if we have enough time, we'll come back to Allan for a few questions. And we are planning for around 60 minutes in total today. Before we move on, just let me say a few words about Surface Ventures. We are a non-for-profit organization, and our mission is to provide you with the world-class surface engineering education for academia and industry. So every month we'll bring you a sector-leading speaker to present the current challenges and future trends in surface engineering. Well, we would like to learn a little bit about our audience today, about you, and hence a very quick poll. So can you please answer the following questions using the poll, which should pop up on your right-hand side right now. And the question is, are you from industry or academia? So if you could just please answer the poll, that would be great. Yeah, you are typing your answers there, which is great, great, okay. Okay. Now you should see an option to press one of the buttons. Great, great. Yes, I can see many answers coming through. At this point, we have 160 attendees, so that's a good number, and I see over 100 already replied. So it looks like we have 2/3 of people joining from academia and 1/3 from industry. That's a good split. Great, thank you for that. Thank you for those answers. Right, so now I would like to hand over finally to our today's speaker, Professor Allan Matthews. So Allan, over to you.
Hi, thanks very much for setting this up, Thomas. Much appreciated. So I'm Allan Matthews. I'm from in beautiful sunny Manchester today, as always. And the title of my talk is digitalized surface manufacturing. And the first question is, what do we mean by digitalized surface manufacturing? Well, this relates to the digitalization of coating processes and the coatings themselves. And the talk will explain why that is needed and the benefits it can bring. And then first of all, I'm going to give you some background as to the reasons why digitalization has been found to be particularly necessary for the coatings and surface engineering sector. Well, there were market studies of the coatings industry, two in the 1990s, and then there was one in 2010 sponsored by the Surface Engineering Association. And those reports confirmed the high value of this sector and highlighted that practices in certain parts of the UK coating industry didn't meet the standards found in other high value manufacturing sectors. The kinds of standards that weren't being met were a lack of product design, integration, a lack of defined and rigorous standards, a lack of what we called intelligence. That was intelligence about market developments, technical choices, coating properties, and process variability, just as some examples. And generally, there was a lack of conformance with characteristics which people expected of high-value manufacturing processes. So as a result of this, Robert Kouachi of the KTN set up a thing called a special interest group. And a special interest group is a mechanism used by the KTN, Knowledge Transfer Network, to examine certain sectors of industry that they feel need special attention or to be looked at more carefully. And in 2014, that special interest group produced a report, and this the title was an examination of surface engineering and advanced coatings. So that's called SEAC, Surface Engineering and Advanced Coatings. And here you see the report that was produced, and the report is accessible online. You'd have to join this Connect organization, and then you can download this report. The report was called Time for Strategic Change, UK Surface Engineering and Advanced Coating Industry. The report, as I said, was produced by a SIG, a special interest group. Why have a SIG? This was for several reasons. One was because of the perceived deficiencies, but also because surface engineering and advanced coating technologies had been identified as one of 22 national competencies in what was then the Technology Strategy Board's high-value manufacturing strategy. And as I said, previous reviews by the industry showed significant market opportunities in key application sectors. So the SIG was set up to identify the technology and innovation needs of the industry and to recommend specific areas where governmental funding would help manufacturing. And just to reiterate, this SIG special interest group was led by industry. The panel that ran it was rightly was dominated by industrialists, with one academic member as well. It looked at the market, the drivers for technological innovations, actions to address barriers to innovation, supply chain characteristics, and then the findings were analysed in a strategic workshop. Just trying to emphasise the size of this market. The coating market in the UK is worth about 11 billion, and there are noticeably big sectors. Paints 3.5 billion, electroplating 2.3 billion. You can see that some of the large ones here. And more importantly, probably, these coatings are used in all of our key manufacturing sectors. So, for example, aerospace uses about £1 billion worth of coatings and treatments. Automotive uses about £2 billion annually. Construction about 3 billion, oil and gas about 2.7 billion. And you can see other key sectors all use significant amounts of coatings. So it is an important sector. It merits being looked at and being helped and being brought to a high level of innovation and competence. As part of the SIG, Keith Harrison and I looked again at the market figures, and we added the government's latest categories and sector definitions, including food and drink, which weren't listed previously. And what we found is that industries with a total turnover of over 383 billion relied on products which were coated. And the actual products themselves that were coated had a value of about 140 billion, which is fairly remarkable considering we're driven there by about 11 billion pounds worth of coatings. So those products couldn't function without coatings. So 11 billion pounds worth of coatings enable the functionality, or the key functionality, of 140 billion pounds of product, which then go on to contribute to industries with that 383 billion turnover. So it's a very, very important sector. Now, this diagram at first sight looks complicated. One of the key drivers within the SIG was David Rickaby. David was with Rolls-Royce at the time, and he produced for us this diagram which illustrates Rolls-Royce thinking at the time about coatings and the coating sector. And what the feeling was that presently, at the time, the focus was on end user resources, reporting the current application supply chain. In other words, where products were failing, they would try to apply a coating, or where they were achieving functionality, they applied a coating. And what they wanted was to the coating sector to integrate with the manufacturing sector to fully get involved in the design of products. And in order to do that, of course, the sector needs to go through the full technology readiness levels in terms of creating standards, validating standards, and introducing process control. And then you can feed the service experience back into the design stage and develop and validate, standardize, and actually bring through a more effective product with a fully integrated coating. That's kind of my simple explanation of what that's illustrating. And that underpins and kind of emphasizes the need for digitalized information about the coatings and about the processes. So what the SIG recommended is certain actions were needed to address those barriers. So what was needed was better performance information about coatings and better accelerated tests about them, more applied and industrially relevant research, a need to address sustainability and environmental impacts of coating systems. Of course, we're all aware of REACH, but there are other health and safety reasons why we need to be aware of sustainability and environmental impact of coatings. And then there was a feeling that we need to improve technology transfer. We need to encourage cross-sectoral exploitation. For example, it was well known that the coatings used in the digital sector, in the devices sector, was well digitalized, but the coatings in the engineering sector weren't. And by the way, those figures that I gave you on the market values were just for the engineering sector, the mechanical engineering sector. They didn't include thin film devices and semiconductors, that kind of thing, which of course are all coating industries anyway, but the deficiency wasn't recognized to be in that sector. It was recognized to be in the mechanical engineering coating sector. And also to provide pilot plant and demonstrator facilities, so-called field labs, where you set up demonstrators in the field with the end users. At the same time, of course, we've seen this rise in the interest in the Industry 4.0. And so it was recognized that you could say that we had Industry 1.0 in the time of the Industrial Revolution. We went through to Industry 2.0 at the time of, say, Henry Ford and mass production. Then we went into what you could call Industry 3.0, where you have PC control and automation. And then now we are really in the Industry 4.0 regime, where we have so-called smart factories, which utilize so-called cyber physical systems to monitor and control manufacturing processes. So the idea that manufacturing then is completely digitalized and carried out on demand and often to near net shape. So we are being very fortunately, in a way, the needs of the coating sector are paralleled with the needs of many other sectors in the industry, and the driver towards this Industry 4.0 and the coatings industry need to also adopt and adapt to that requirement. This is reflected, by the way, in government policy. In the government policy paper in December 2018, the policy was set out that we had to strengthen the UK and lead industries in the future via what they call 4 pillars or grand challenges as drivers of productivity. So within these are the 4 pillars, and within the 4 pillars you can see AI and data as being key. And the government policy states that those 4 pillars, which include mobility, aging, and clean growth, will drive an increase in productivity under the headings of people, ideas, business environment, infrastructure, and places. That was underpinned by something called the Made Smarter review, which estimated the benefits of adopting industrial digital technologies to be up to 455 billion in the next decade for the UK manufacturing sector. Now, we've said that the coating sector is worth about 11 billion and related products about 140 billion. But in terms of the academic lead, although it's recognized throughout the world that the UK has some of the best academic research in coatings and treatment processes, it was also recognized that no single UK university has all the required interdisciplinary expertise, and there's a lack of connected knowledge in the area of digitalisation in surface engineering. Another point made in the Made Smarter review was that the UK is lagging behind other advanced nations in overall productivity. It could be measured in output per worker or whatever measure you wish to apply to it. But it was felt that that was due in part to the lower levels of adoption of digital and automation technologies. And that was particularly acute amongst the small and medium enterprises. Now, when people talk about improving productivity, they often talk about the 7 wastes. And if you go online and you do a Google search on 7 wastes, or even 8 wastes is another jargon, you see diagrams like this. This one's taken from this source, but there are many out there, and I've extended on that particular one. But the wastes include overproduction, too much inventory, too much transportation, too much motion of people carrying things around, waiting for things, waiting for raw materials, waiting for product to come through, defects, and over-processing. So of these, you could say that overproduction, defects, and over-processing are key. And if we can reduce these, then we can increase the added value and we can increase the productivity of industry. And this idea to get these aspects under control is no more important than in the coating sector. And to do all that, you need to have absolute digitalized knowledge about your production, about your coating, about your inventory, your transportation. Everything has to be fully digitalized. So in order to digitalize, they call it the digital gap. You know, how far is industry short of being fully digitalized? But if you can close that gap, you can get better utilization of your assets. You can reduce your dependency on tacit knowledge. You can reduce the time and cost linked to product verification. You can improve and give visibility to all business performance metrics like the yield, right first time, cost, delivery, quality, and equipment effectiveness. And you can fully enable and improve design for manufacture. You can open up new business opportunities and provide a framework for developing improved business as well. So that's kind of explains why we need it in academia. We need to improve what the research we do to achieve those benefits. But also, as I said, that report, the SIG report, was driven by industry, and fantastically, actually, the industry has grasped this challenge and has created itself something called SELF, the Surface Engineering Leadership Forum, which is an industry network, and the industry network SELF will work closely together with the new EPSRC, Digital Surface Manufacturing NetworkPlus. So the NetworkPlus is a £1 million investment by the EPSRC to bring together the diverse expertise and capabilities in UK academia to enhance digitalisation in surface manufacturing and move the sector forward to meet those Industry 4.0 challenges. And it will be done in very close collaboration with SELF. And more about that later. So the Digital Surface Manufacturing Network already has, well, at the time that we applied for it, had 60 members. It's now got more than 100 members from over 36 organisations. The main academic teams are at Manchester, Queen's University Belfast, Sheffield and Cranfield, and Swarav has just moved to London South Bank, so we've also got London South Bank University involved. And the network partners include SELF, the Henry Royce Institute, the MRC, MTC, MAPP, and importantly, the Surface Engineering Association. So that's the main industry body with several hundred members, mostly small and medium enterprises. And we've also got a number of coating manufacturers on board also, and we're getting more on board all the time, but the main ones that came on board when we started were Woolwork, Poetons, Monitor Coatings, TRL9, Thin Metal Films, and also Micromaterials. And you're going to hear some words from Micromaterials straight after me. So the objectives of this NetworkPlus are to well, there's many and various, but we aim to identify and benchmark the UK capabilities. We want to enhance the capability by introducing digitalisation and promoting the cultural change in academia, so academia understands the digitalisation concepts and needs. To provide a sustainable forum for discussion to enhance cross-sectoral learnings, establish a well-informed and aware multidisciplinary research community that's agile and committed to move the sector forward into the new Industry 4.0 age, to support fundamental research and feasibility studies and demonstrator projects. And hopefully, we hope to be the go-to place for advice on digital technologies and in the coating sector. So some of the things that the network will do: it will encourage networking. These will be network-wide events, focus workshops, and expert groups to tackle targeted challenges. It will fund and support feasibility studies that will hopefully leverage additional funds, and particularly we want to address the needs of early career researchers and encourage them to get involved in this kind of revolution in digitalisation, and to demonstrate the potential to improve technology level of coatings and processes. So kinds of examples of feasibility studies are given here. They're just examples: self-repairing processes and coatings, root cause analysis and fault detection, digitalisation of coating processes, process statistics, processes for whole cycle or life cycle cost reduction, control techniques for in-process verification, new digitalisation technologies for imported from the devices sector, coating process improvements in all of the functional ways that coatings can be improved. And demonstrator projects, which I mentioned, they will include things like the production of predictive digital twins, multifunctional coated surfaces, multi-objective optimization, automated masking, in situ non-destructive inspection, and in situ measurements. Again, just as examples. Training and development will be a key part of the NetworkPlus. It will involve mentoring. There'll be fora for early career researchers in particular, secondments of people, academics into industry and industry into academia. There'll be a summer school next year. And the Digital Surface Manufacturing Network will work with SELF on its new apprenticeship program, which is, I would say, was largely being driven by David Rickaby. And David was telling me yesterday, as a key part of level 7 of the apprenticeship program will be to address the 7 wastes. So if you want your people to understand, address the 7 wastes, then please get them started on the SELF apprenticeship program, which is fully validated and conforms to all of the apprenticeship requirements. The network structure, well, there's a management team, which is myself, Adrian Murphy from Belfast, Ashutosh Tiwari from Sheffield, and Swarav Goel from Cranfield and London South Bank. Our industrial representative is Brian Alcock, and our network manager is Pamela Sharma. There is also an independent advisory board incorporating David Elliott from the Surface Engineering Association and from SELF. From academia, we have John Nichols. An international representative is Jose Luis Andrino, who some of you may know, was at Cranfield and is now in Spain. For the EPSRC, we have Becky Chisborough. And for government agencies, we have Robert Corshire, who, as I mentioned, has been a very strong advocate for surface engineering in the higher corridors of government, and has been most effective in getting improved funding for research into coatings and surface engineering. The networking activities and horizon scanning will be under the guidance of Adrian Murphy at Queen's Belfast. The fundamental research and feasibility studies will be overseen by myself. Ash Tiwari at Sheffield will oversee development of demonstrators with industry, and training and development will be under the leadership of Swarav Goel. We want to work together. We want to work together with all universities in the UK who are involved in coatings. This diagram by no means includes all universities that are doing coatings. There's some, as I said, there's some excellent work being done in many universities in the UK into coatings. And so if your university is not listed there, it's not because we aren't aware of what's going on, but you know, we can't fit every university on that diagram, but we want to have everybody who has an interest in coating in academia to join this group or this network, and we can work together to develop good research projects and get funding for those projects as well. As I said, we shall work together very closely with SELF and organise joint events, and because we have the same interests in improving the knowledge of digitalisation, both in industry and academia, we'll work together on that. This is some of the members for SELF, and as I mentioned, the SEA in itself has many hundreds of members, so SELF represents many hundreds of companies, and they're integrated, or they're working closely with the DSM network. Now, one of the drivers of SELF has been Brian Alcock. I'm sure many of you know Brian. Brian developed the company Monitor Coatings before selling it, and now has a company called TRL9. And Brian also has been a tremendous advocate and has helped the sector. And one of Brian's main messages is that this sector, which is worth about 11 billion, is set to grow significantly by 2025. Most predictions show it to be growing to a level of 25 billion by 2025. So this diagram shows the potential growth. The lower bar is the current level of use of coatings in these sectors. And the use of coatings, of course, is end user driven, it's sector driven. So a lot of these sectors have realized they will need to use more and more coatings in order to achieve the functionalities that they need. And Brian's message, very powerful message, is if we don't adopt digitalization, we won't be able to access these growing markets, and the productivity and profit will go down. But if we do go through a transformational change and we adopt these digitalization practices, the sector will be able to address these growing markets, and the profitability and productivity will improve. Brian also presents this in this way, or the people that work with Brian, including Dave Rickaby, and talk about a transformational change. So moving from being match fit to being best in class to being world class, you need to go through a series of stages in order to win and move forward. You can look first of all at core activities like operational improvements, addressing the 7 waste methodologies, moving towards the digital, filling the digital gap, implementing digital manufacturing, till eventually you move to a full design for manufacture, fully transformed industry, applying design for manufacture. So that's the transformational route that we intend to go through, both within the digital surface manufacturing or digitalized surface manufacturing network and within SELF. Again, this is one representation from Brian that you can actually you can go for the low hanging fruit to begin with, do the normal things that are known about lean engineering. You can go through the well-developed statistical process control route. Then you move into design for of experiments type approach until you eventually go through to the design for manufacture and design for assembly and robust designs. So that's the way we're taking the digitalization. Of course, there's nothing very new in this, but I mean, often you find that people reinvent. I know that statistical process control really took off in the 50s, but my thinking is now that with full digitalization, we can fully access the benefits that we're all aware of that you can achieve from statistical process control. Some aspects of control, which this is a slide which Brian sent me, and which I again, David was telling me that this is very much also his input. You start off by looking at predictable performance, looking at asset care, control of inputs and process failure modes and effects analysis, look at the process basics, have reaction plans if things go out of control, and be ready to accept that when you introduce your reaction plan and you don't get it back in control, then you've got to rethink the whole process. You've got to also look at variation reduction, or this will come from this first stage. Look at process variability and key performance variable strategy, again, continue with process failure modes and effect analysis in your variation reduction, and then go into your engineering attributes, your engineering standards, control strategy and validation in order to ensure that you meet cost and quality requirements. And this is the kind of thing that's been implemented over some years. This shows one particular manufacturer, how they've managed to bring the variability well into control using asset care, in-process checks and compliance audits, and in-process verification. So this is the, if you like, the underlying understanding of what we need to do. And in order to do it, we need to have digitalization. And all this is part of what they call the industrial Internet of Things. You've probably all heard of the Internet of Things and wondered what it means. It's all to do with using the internet to connect factories, to have inventory management analytics, to have preventative maintenance, visualization, plant safety and security, quality control, improved logistics and supply chain optimization, and then new business models. And again, without reiterating the obvious, this absolutely requires digitalization. You can't do any of that without digitalization. Digitalization effectively links the digital world with the physical world. And this is a slide which I got from Swaraj Goel, and it's a part of a keynote paper from Richard Leach at the CIRP, which is the main production engineering research organization. So basically, digitalizations that use a virtualization of reality is one way that was stated. So we attempt to understand a machine's function by creating a digital blueprint of its reality. So everything you see is represented digitally. And again, coming back to Brian, what Brian Alcock has done, he says that his best operators can see and hear when a process is operating well. But of course, you can't rely on the subjectivity of the operator. So what Brian has done very effectively is he's introduced these so-called cyber physical devices, sensors within his process, to observe the process and to listen to the process, and to ensure that his processes are under control, fully digitalized via these cyber physical devices which monitor the process. At Manchester, we've done quite a lot of work on the plasma-assisted electrolysis process, and these slides are from Alexei Rogov and Alexei Yorokin. Alexei leads this group, and for plasma-assisted electrolysis, we can remove material, for example, by plasma polishing. We can modify material through, for example, cathodic and anodic plasma treatments, and we can convert surfaces, for example, through plasma electrolytic oxidation. So basically, you combine electrode reactions with high energy species from the plasma. You can spontaneously initiate the process if you apply sufficient voltage, and you can get local heating, and the energy dissipated at the electrolyte interface allows you to convert the surface of that electrode. Quite a powerful technique. It's fast, it's no pre-treatments, better protection, compatible with complex shapes. It's very safe, there are no toxic elements involved in it, and you can produce a wide range of surface properties. The drawbacks of it, and this is what lends itself to digitalization, it's a complex process. The mechanisms are somewhat uncertain. It's very empirically based. It has a high energy consumption. You spend a lot of power heating the water-based electrolyte. It uses rather specific non-standard equipment and has adopted in the past a rather trial and error approach with rather expensive R&D practices. Just to illustrate, there's actually a video in from Russia, actually. Now, the PEO process was actually developed in Russia, and there was a video showing somebody trying to build an all-aluminium engine and to plasma electrolytically treat it. Now, you can imagine the challenges of trying to optimize the coating on all of these different kinds of parts. So what you've got to do is go back to your basic equipment that's involved in your plasma electrolytic process and fully digitalize it and link it. So you've got your power supply, the electrolyzer itself, the cell, the specimens, the sensors, the digitalizer, the data logger, and then you've got other features like cooling and gas extraction. And what Alexei Rogov has done has really draws on the capabilities of digitalization. So what he has said is that you've got to develop a G model, that's your geometry and your shape. You've got to develop a process model, which he calls the P model. You've got to bring together the P and G models. You might even incorporate 3D printing into production of your part, and then you go through to production in a very controlled way. Well, very difficult to do this, of course. This is the scientific problem, and there's an engineering problem, and that relates to how do you link all this into your cyber-physical device. And this is something that Alexei has managed to do. He's managed to link together the process and geometry model, which represents, if you like, a scientific problem, and the linking together with the cyber-physical interface, and linking these in a rather iterative way, which gives you the control you need. And the key to this is to create what they call a digital twin, as I mentioned. So you need a software-based model of the manufacturing process. You've got to be able to follow the behavior of the system through all steps of the fabrication. You've got to optimize the digital form and have a reference manufacturing pathway with full quality criteria. Now that, just to illustrate what that means. So in normal, traditional production, you produce something and then you test it. And if it doesn't conform to the quality criteria, basically you reject it. You don't monitor faults during process, and you could easily produce junk. If you can go some way to overcoming some of that by having intermediate progressive testing, but even then you could well produce defects which you can't correct during production. However, if you have a full digital twin and you follow your production, you can do it virtually to begin with, or all the steps of the way. You can actually monitor defects or the effective creation of defects on a microsecond basis. And that's the core of digitalization and the benefits of the digital twin. And another diagram. So the old adage is it's better to build good quality in than test bad quality out. And what this one does is you could easily produce bad quality and you just have to basically scrap it. With this, you ensure that you always produce good quality and you're in total control of the process. So another diagram here from Alexei Rogov. You will have your ideal manufacturing pathway, and then you will monitor it. This can be in the shape of a digitalized twin, if you like, of the real process. And you can run through your digitalized twin process or the real process by monitoring with your cyber-physical device, and then utilizing your digital twin to monitor when you're going out of control. Now, that might seem like an abstract concept, and it is rather abstract, and it's difficult for people to kind of often to get their head around this, but it works, and it works very effectively, and it really does illustrate very powerfully the benefits of full digitalization and the building of the digital twin. So it illustrates how an intelligent manufacturing pathway can be devised and followed. That's basically a trajectory of the process parameters available for automated tracking and decision-making under in-situ manufacturing control. So fundamentally, as I said, it incorporates a digital twin, a complete model from which a certain solution can be derived. And of course, there can be many pathways. And the beauty of this is you can easily revise the pathway depending on the requirements of the surface properties for different applications. So just to, last slide but one now, just to reiterate what the NetworkPlus will do. It will encourage academic research in this field. It will improve process and coatings and modeling. It will facilitate state-of-the-art coating facilities, drive improved digitalization in the coating sector, the processes and the coatings, implement improved characterization analysis, improve performance evaluation and test methods, accelerate fruition of new innovations to market, enhance coating throughput rates, facilitate full life cycle analysis for coated products, and this list is extending all the time. And I think hopefully I've turned you on to the benefits of digitalization, and you can see that it is phenomenally powerful, and it's going to give us all kinds of benefits. However, we're only just starting this journey. The route to full digitalization is very challenging, as you can probably tell from what I've said. But now we have a clear understanding of the challenges and the determination to succeed. We've got a roadmap and a strategy. We've got key participants on board. We're aligned with governmental strategies, with research council strategies, and very importantly, with the industrial strategies. And we really do hope that you will join us in this journey. So thanks very much. That's the end of my talk.
Allan, we are that very informative presentation. There are a few questions on the side in the dialog box, so if you don't mind, we'll come back to those. And now I will hand over to Adrian from Micromaterials for a few minutes. Adrian, over to you.
Good morning, everybody. Well, morning, I guess. So thank you very much for inviting us to have a few minutes in this webinar this morning. So I'm an applications engineer with Micromaterials, and we specialize in nanomechanical testing equipment for materials testing properties. So a lot of our equipment is really focused on coatings development and monitoring properties of coatings as they're developed. So I just want to introduce really what our capabilities are, just really literally 4 or 5 minutes. So we have a whole range of different test techniques. So what are they and what can I do with them? Well, we have indentation, okay, so instrumented indentation, and that's used for measuring hardness and elastic modulus of materials. We can measure mechanical properties at any given point on a surface. We can measure properties across a surface to create a mechanical property map, and we can look at properties of surfaces as we get further into a material. So we can start at the surface and see how these properties change with increasing depth. So you can see here we have some mechanical property profiles for some coated samples, something 40 nanometer and 80 nanometer hard coatings on some glass substrates here. So so indentation is used for that, and we can also work at larger scales, so micro indentation up to 30 newtons for looking at bulk properties of materials as well. So we're not just limited to working at the very, very small scale end of hardness testing. Importantly, also for coatings and for bulk materials is tribology. So we move into then nano and micro scratch and wear testing. So this enables us to look at properties like friction, the adhesion of coatings to surfaces. Obviously, you know, it's one thing to develop a high performance coating, but it's another thing sometimes to achieve a good adhesion of that coating to the substrate, and without that adhesion, essentially the coating property, the coating is compromised in what it can offer in an engineering system. And we can look at critical failure events and loads at which they occur. And so that's quite an important thing along the development path, because two nominally similar coatings, if deposited under different conditions, can actually undergo very different failure mechanisms to each other. And we could start to understand what's controlling failure and causing failure through scratch testing. We have some other tribology techniques as well, which bridge the gap between scratch testing, which is a single contact high pressure loading tribology test, bridge the gaps between scratch testing and what we might regard as traditional tribology work with things like pin on disc tribometers. So we have some reciprocating sliding tests at different scales. So we have nano fretting, and we have a device called nano tribo test, which allows us to do reciprocating sliding up to tens of millimeters sliding distance scale. So again, we can study friction, we can study wear as well with these techniques. So we have different tribology techniques for different scales of interest. Okay. Moving along the strain rate scale, so the strain rates associated with indentation testing and scratch testing are pretty low, but of course a lot of materials are subjected to very, very high strain rates in their real world application, and it's very, very useful to be able to replicate those strain rates at the lab scale during the development process, coatings and bulk materials. So with these techniques, nano and micro impact, we can create single or repetitive very high strain rate contacts to look at toughness, fatigue resistance, and effective hardness, high rates of strain, which we call dynamic hardness. There are other techniques as well which we can use, and these three techniques tend to be used a little bit more in academia for fundamental characterization of materials. So certainly micropillar compression and micro cantilever bending are used with a variety of different materials, ceramics, metals, etc. In this particular case at the bottom, what we're looking at here is the effects of ion irradiation of tungsten alloys for nuclear power. So it's important to use the small scale technique here, because the ion irradiation process only affects a few microns of the sample surface. So the micropillar compression similarly allows us to interrogate a small volume of material, and because we're working with a fixed volume of material, this is rather like a nanoscale tensile or compression type test, where we can convert our load and displacement data directly to stress strain very, very easily. We can also work with materials other than bulk and coatings, including composite materials. So here we're looking at debonding forces in fiber reinforced composite materials. So we actually use a flat indenter to push fibers out. So coatings are a very important part of what we do, but we can also work with a wide range of other material types. What materials themselves can we actually work with? Well, basically anything. So nano indentation was originally developed really for characterization of thin coating materials, but it's been developed a long way in about 30 years. It's been available as a technique, and we can work with biological tissues, polymers, hard biotissues such as bones, metals, composites, semiconductor materials, ceramics, and even diamonds. It's actually possible. It seems a little bit counterintuitive, but to perform successful hardness and elastic modulus tests on a diamond sample using a diamond indenter. And as we already mentioned, the samples can be bulk, they can be coatings, they can be surface modified layers, etc. Also important in lab scale testing is the ability to, as closely as possible, replicate in service conditions. Now, most of the work that people do with nano indenters is in air. Okay. However, of course, we know that material properties can change very significantly with exposure to different environmental conditions. So that could be fluid submersion, it could be exposure to high or low humidities, high temperatures or low temperatures, even electrochemical conditions. So, you know, in a corrosion or a plating type environment. We can, when we're working at high temperatures, we may need to protect the sample from oxidation to replicate an in-service condition. So we have strategies to achieve that as well, including a gas purge chamber and a high vacuum nano indenter called the nano testing stream. So just a summary. So mechanical testing across the nano, micro, and macro scales is possible with our equipment. So go from 10 micronewtons up to 30 newtons. Multiple techniques, including indentation, scratch, wear, friction, impact, etc. Any material type can be tested. We can work with bulk samples. We can work with coated samples, surface modified layers, etc. We have the widest range of testing environments offered by any manufacturer, we believe, to further make tests as industrially relevant as possible. And we have a highly experienced applications team who are available for consultation. So whatever material testing properties you have today, coatings or other, then don't hesitate to contact us and we will see if we can help you. I'll just leave you with an overview list of the various things that we can offer here. So Great. That's all I've got to say this morning.
Thank you, Adrian. Thank you. Much appreciated, and thank you for your support. So only a couple of minutes left. So if we could come back to you, Allan, and I picked up some questions here. So Chris is asking, how do you define coating within the framework of your work? Is it only one particular technology, or it's more broadly?
Oh, it's all technologies. You know, Dave Rickard has made a comment, which is I tend to normally only talk about PVD and plasma processes, but by no means is this exclusive. It's all possible coating techniques, all possible surface modification techniques and treatments, anything that can enhance the surface, basically. Well, with the proviso that we feel the digital sector, so the devices sector, I should say, is well covered by digitalisation. Mm-hmm. What we're aiming to address is the mechanical engineering coating sector, so mostly wear, friction control, corrosion, etc.
Mm-hmm. And Lawrence is asking about AI and machine learning for development of new coatings and technologies.
Yeah, well, I mean, I didn't use the term machine learning, but that is effectively what's being done with that that work on the the plasma electrolysis process. It's using machine learning.
I think Jean asked about the possible membership in Network. So how people can interact with Network?
They absolutely just go to the website. It's on at least one of the slides. If you search digital surface manufacturing, you'll get to our website. You just sign up there. There's no charge, and you can give as much or as little information about yourself as you wish. Pamela Sharma overlooks that, and she'll be available to answer any questions about it.
Thank you, Allan. So we exhausted time. So I would like to thank you for delivering the presentation and this inaugural Surface Ventures webinar. So thank you for that, much appreciated. I would like to thank Micromaterials and Adrian for their contribution. And just to remind everyone that you will get an automatic email with a link to the recorded webinar if you want to revisit what was discussed today. And in a few weeks, we'll plan the next webinar. So please stay tuned and keep an eye on your inbox, and we'll bring another speaker, an exciting topic to discuss in a few weeks. So see you next time. Thanks for now. Thanks for joining, and have a great day. Bye.